Hello and welcome to today's seminar in the Smart Mobility Connection series. My name is Carlee Benhart-Kukula and I'm the 2019 Traffic 21 Women in Transportation Fellow. The Smart Mobility Connection series is sponsored by the Traffic 21 Institute and the Mobility 21 University Transportation Center as an opportunity for faculty to showcase their current transportation projects. It is also an opportunity for students, fellow faculty, deployment partners, and the broader community to engage and network with researchers, highlight opportunities for development, and foster future interdisciplinary collaboration. Please note this session is being recorded, and all participants' microphones are muted. To ask a question, please send a message through the chat box. You do not need to wait until the end of the presentation to send your questions. Now I would like to introduce today's speaker, Carlee Joe-Wong. Carlee Joe-Wong, an assistant professor of electrical and computer engineering at Carnegie Mellon University, received her AB, MA, and Ph.D. degrees from Princeton University in 2011, 2013, and 2016, respectively. From 2013 to 2014, she was the Director of Advanced Research at DataMi, a startup she co-founded from her PhD research on mobile data pricing. She has received a few awards for her work, including the ARO Young Investigator Award in 2019, the NSF CAREER Award in 2018, and the Informs ISS Design Science Award in 2014. Please help me welcome Carlee as she tells us about her University Transportation Center project, Incentivizing Taxi Movement for Balanced Citywide Services.
All right, thank you very much for the introduction. I'm very happy to be here and thanks so much for having me. Let me just set up the screen here. Okay. All right, can everyone hear me okay and see my slides?
Yes, we can.
All right, great, thank you. Yeah, so I'm very excited to share some of my work on incentivizing taxi movement for balanced citywide services. This is an ongoing project and it's joint work with several people. And I particularly want to highlight the contributions of Xinlei, Susu, and Xiaoxi, who have been working on this project for several months now, and they are really the ones responsible for most of the work here. All right. So let me first try to sort of explain what we're trying to do and motivate the problem, and then I'll get into why we care about incentivizing taxi movements. So the motivation for our work comes from this idea that cities are increasingly offering sort of what we call city scale services. And by that, I mean things like taxi or ride sharing services that are offered kind of throughout an urban area, things like pollution sensing or environmental sensing that again are offered sort of throughout a city or throughout an urban area. And the things that these services have in common is that they require this broad spatial coverage. So you really need to have, for example, taxis spread across a very large area, or rideshare providers spread across an area. And if you're doing environmental or pollution sensing, you need to have sensors spread across a large area. So this is an image I grabbed from the Breathe project, which operates in Pittsburgh, and it's showing black carbon concentrations sort of throughout the Pittsburgh area. And you can imagine that to get a map like this, you really need to be able to sense what is going on all around this area at a fairly fine spatial and perhaps temporal granularity. So this is kind of a fundamental requirement for many services today. And throughout this talk, I'll mostly be looking at environmental, specifically pollution sensing as an example. This is an example application that we actually deployed in China. But many of the techniques and some of the ideas could be applied to other city scale services such as taxis or ride sharing. So the problem that we started considering was how can we ensure such coverage in practice? And really the first thing that we were able to see was that if you want to do kind of city scale sensing, dedicated citywide deployments are expensive to build and they're expensive to maintain. So imagine, spreading like carbon or pollution sensors throughout this entire area. That's kind of a big job, especially if the sensors are expensive or difficult to set up, as they often are in practice. So just kind of setting up this dedicated deployment is maybe not a feasible solution to providing these services. A natural alternative way that you could provide these sorts of services and ensure this sort of broad coverage is by taking advantage of mobile nodes. So for example, vehicles that kind of naturally travel throughout an area and may give you some of the spatial coverage that you're looking for. So for example, this is an image that I took from Uber, one of their blog posts yesterday. And this is showing the vehicle destinations from their headquarters in San Francisco. So you can see that if, for example, you were able to mount a sensor onto each of these Uber cars, you would actually get some fairly decent spatial coverage in the city of San Francisco, because these cars are going to all these different destinations throughout the city. And even a few destinations outside of the city, although clearly it's much more sparse outside the city. So we started, once we started noticing this, we started thinking, well, is it possible to really take these sorts of mobile nodes, mount sensors on them and use them to provide the spatiotemporal city scale coverage that you need to provide these kinds of urban or environmental sensing services. And as you can see from the image here, the answer is kind of a qualified yes at first glance. So yes, you can provide some spatial coverage, but you may still have kind of suboptimal coverage in some areas. And this is not just a problem for environmental sensing. This could also be a problem for, say, transportation services. For example, if taxis or cars concentrate in sort of richer areas of the city, that could result in unfair access to transportation for other people in other areas of the city. So this is a general problem. And I've sort of hinted that we decided to use this idea of mobility as a solution to achieve this kind of coverage. So the idea here, again, is that vehicles sort of naturally move around the city over time, and they can be used to carry sort of sensors or passengers. And as we started to think about this, we started noticing that there are different types of vehicles that you probably have to take into account. So some vehicles are fixed route. So for example, buses, trains, mail carriers, they sort of follow the same route throughout the city, more or less at the same time every day. On the other hand, you then have other types of vehicles, which have what we call variable routes. So these would be things like cars, these would be things like taxis, that may drive to different parts of the city at different times of the day, and this will vary from day to day. So here I'm just showing an example of bus routes in Pittsburgh. You can see that the buses sort of cover many parts of Pittsburgh, but maybe not all of them. And here's a schematic of how, say, taxis kind of move between different areas of the city over a day. So initially we thought, well, maybe fixed route vehicles would be enough. So for example, if I could mount a pollution sensor on every bus in Pittsburgh, would this be enough to get me sort of all the data that I need to collect or to make a pollution map of the city? And as it turns out, the answer is this is not necessarily enough, and it may not be quite enough. And there are several potential reasons for this. One is for some applications, you may need data that is sensed at regular time intervals that are kind of finer granular than, say, a bus driving through the city. You also have this issue that areas kind of between the bus routes are not covered terribly well. Now, maybe that's not an issue in, say, downtown Pittsburgh, but it could be an issue, for example, in some of the suburbs. You can see here in this map that some of the suburbs are relatively sparsely covered by these bus routes and by sort of fixed route vehicles. So that means that then you have to turn to variable route vehicles. And once you do that, you get into this very interesting question, which is really the core of this talk, which is that if you have a vehicle who is willing to change its route from day to day, from time to time, you may be able to incentivize that vehicle or incentivize the driver of that vehicle to change the route so as to ensure that you get the spatial coverage of the city that you want. So this is really the question that we're trying to answer in this talk, and hopefully I've motivated for you why we care about it. How should we offer incentives that change driver behavior, that incentivize them to go to different areas of the city so as to achieve our coverage goals for the city scale service? So there's many different ways to start offering incentives, and there's been some work looking at variants of this problem. In this talk, I'm going to be talking about two particular ways that you could try to offer incentives to vehicles to incentivize them to change their behavior. So the first way is relatively straightforward, but a little bit more difficult to deploy. And this is what I call trajectory-specific incentives. And the idea here is for each vehicle, you can specify sort of a sequence of locations at which you would like this vehicle to, say, collect data for you. And then your problem becomes, well, which sequence of locations should I specify for each vehicle, and how much should I pay them to actually follow that trajectory for me? And the idea is, if you set the payments correctly, then the vehicles will say, okay, I'm willing to, drive along this route for whatever amount of money you pay. Now, as I said, this is sometimes difficult to implement in practice. So we've also more recently started looking at what I call location-specific incentives. And these are not tied to a sequence of locations. These are just saying, if you're a vehicle and if you sense data for me at this particular location, here's how much I'm going to pay. So this is, in some sense, much simpler to present to drivers, because you just tell them, if you give me data at this location, here's how much money you get. And then the question becomes sort of how much should you pay for data collected at these different locations? All right, so before I get into the details of how we answer those questions, of how we determine these incentive amounts, I wanted to talk a little bit about some of the related work, because we aren't the first ones to look at mobile crowd sensing. There is a wide body of work that looks at the problem of selecting vehicular or mobile sensors. And the idea here is that you have a bunch of vehicles, they're sensing data for you, and they're moving at kind of predetermined routes throughout the city. And you may or may not know what those routes are, but those routes are not something that you are able to influence. So this is clearly a related problem, but it's a little bit different from what we're trying to do, because we assume that we can control this vehicle mobility. We can incentivize vehicles to change their trajectories and change where they go. There's also been a lot of work on sort of the theory of how do you incentivize vehicles to contribute data, or more generally, how do you incentivize people to contribute, say, sensing data to your system. And we've borrowed some ideas from this literature, but again, this literature tends not to take into account this idea of influencing where vehicles go, and the sort of spatial coverage that you achieve by influencing where vehicles go. And then finally, there's been some work on sort of using reinforcement learning techniques to try to optimally distribute vehicles throughout the city. This has particularly been used for ride-sharing services. So using reinforcement learning to try to tell drivers in ride-sharing services sort of where to go so as to pick up the most passengers throughout the city. So this has kind of a similar flavor of sort of incentivizing or directing vehicles as to where to go. But of course, the objective is much more different. So we're not trying to optimize the profit of a ride-sharing platform. We're really just trying to ensure sort of good spatial coverage throughout a city so that we can offer these sorts of city-scale sensing or other services. So we borrow some ideas from this work, but our perspective on this problem is a little bit different. All right, so on this slide, I'm just trying to give you sort of an overview of what we've been doing and an overview of the talk, and then I'll go a little bit more into detail about exactly how we accomplish our goals. So the first part of the talk, I'll be discussing sort of how do you model vehicles, how do you model spatial coverage, how do you optimize the incentives that we offer to these taxis so as to ensure good spatial coverage? And what does good spatial coverage mean? On the second part of the talk, I wanted to present a taxi mobility simulator that we've been developing. And this allows us to sort of evaluate what is the effectiveness of these incentives that we're trying to optimize with our vehicle and coverage models. And then in the last part of the talk, I wanted to show some simulation results, and we actually have some experimental results as well. As I mentioned before, we tried out some of these ideas on a deployment with taxis in China. All right, so for the first part of the talk, as I said, will be about theoretical models and how we actually optimize the incentives we offer to these taxis. So our first task here was to start thinking about qualitatively, how do incentives affect taxi movement? And in this part of the talk, the vehicles that we'll be talking about are mostly taxis. So the idea is you have kind of sensors mounted on taxis and you want to ensure that they spread across the city in some sort of good way so you can get your sensing coverage. And we chose taxis because the incentives of taxis are relatively easy to understand. So in particular, if we don't offer any incentives, if we just sort of mount sensors on taxis and tell them to go places, wherever they want, then the taxis will tend to move towards locations of likely ride requests. So the drivers will want to sort of go to places where they can really pick up passengers. And of course, our idea is to offer monetary incentives that may kind of change their trajectories. So this sort of cartoon here kind of illustrates these ideas. So with no incentive, maybe the taxi goes to this part of the city here. If the driver knows there's a ride request over here, then probably they're going to change their trajectory and go to pick up that ride request. If we offer some monetary incentive, then the driver might say, all right, I want to go here to pick up a potential passenger, but you're offering me money to sense data for you in this location, so I'm going to go through that location, and then I'm going to pick up my ride request. So this is kind of a simple illustration of how incentives can alter taxi movement. So our idea, of course, is to optimize those incentives so that the movement is offered in some kind of good way. But in order to do that, we have to have some measure of what is sort of a desirable trajectory, what is our desired coverage of the city. So many prior works on this assume that the goal is an even distribution of sensing and an even distribution of vehicles over space and time throughout a city. So intuitively, if you want to get a pollution map like this, you might think you might want to do that. However, there are cases where an even distribution is not the best thing to do. So for example, you may have sort of some dedicated sensors at some parts of the city that are very accurate, and you may want to collect sort of more data at those locations to kind of calibrate the sensors you've mounted on all these taxis. There may also be scenarios where in some areas of the city, whatever you're sensing is very stable, so you don't need very many measurements. Whereas in other areas, you may have very unstable measurements. You might have a lot of noise, so you may want kind of more vehicles to go there so you get as much data as possible. So to accommodate these kinds of cases, we decided to define balanced coverage relative to a given target distribution of vehicles or data sensed throughout the city. So mathematically, these are the expressions we used. So here, this O of ijt is a target distribution over locations I, J, and times T. And this metric here on this first line is something called the KL divergence. And this is comparing the target distribution over locations and times to the achieved distribution over locations and times. This PIJT denotes the achieved distribution. This is a function of where each vehicle goes, that is the trajectory of each vehicle. And I'll explain on the next slide how we model these trajectories. And the KL divergence sort of measures the difference between them. The idea is to minimize the KL divergence, that is to get this achieved distribution P as close as possible to the target distribution O. So that's sort of how we quantify our notion of balanced coverage. And now we see here that since our achieved distribution is a function of the vehicle trajectories, we would like to offer incentives so that these trajectories sort of steer P to achieve a low KL divergence. Now, in order to do that, we have to model a little bit what are the vehicle trajectories and how are they a function of the incentives we offer to each vehicle. So on this slide, I'm looking at trajectory-specific incentives, which again is the case where we specify a sequence of locations for each vehicle and we attach an incentive to that, that sequence of locations. And if we've done this right, then hopefully our incentive will successfully influence the vehicle to travel along our specified sequence of locations. So to do this, we model a trajectory as, let me take a step back. So to do this, we have to model a trajectory, and we do that by dividing our city into a spatial grid. So here, this is just a square grid over a city. And we specify a sequence of locations by saying the agent or the vehicle should be in this specific location at this time, this specific location at the next time, etc. So you can think of this as kind of specifying on this three-dimensional grid as shown here, where a vehicle should be at each time and at each time. And now, assuming that we know where we want the vehicle to go, we would like to say, well, what incentive do we need to offer the vehicle in order for it to travel along a given trajectory? And the idea here is we use this expression, which I'll try to explain, at least qualitatively. Basically, what we're trying to do is we're trying to compare what is the reward that a taxi could get from sort of following its default trajectory, and what is the reward it could get from following our controlled trajectory. And when I talk about reward, what I mean is, remember at the very beginning of this, we said that taxis are influenced by the ride requests. They want to go towards where they can pick up passengers. So if we're trying to get the taxi to go along a trajectory where there's a lot of passengers that they could pick up, we probably don't need to give them much incentive to do so, because they might do that already, because that already aligns with their given incentives. So what we try to do is we try to say, well, suppose we sort of know where the, what is the trajectory with the maximum number of ride requests. This is a trajectory the taxi would take by default. Then when we steer the taxi towards another trajectory, we are in some sense depriving them of some potential revenue because our specified trajectory might have fewer ride requests. So the incentive we offer the taxi is calculated to exactly make up this difference, to exactly make up the expected difference in revenue from following the trajectory we want compared to what the taxi would do otherwise. And that's what this equation is here. And this RC control minus RC rand is this difference in reward that I was talking about. And then there are some thresholds on sort of the minimum and maximum incentives that we offer to the taxi, which I won't go into for the sake of time. So this gives us the incentive that we would need to offer to each taxi to get it to follow a specific trajectory. So now this allows us, coupled with our measurement of what is good balanced coverage, to formulate an optimization problem. And here our objective is, again, this KL divergence. So this, so we're trying to minimize the KL divergence to ensure good coverage. And we do this subject to some constraints. So this constraint is just the relationship between the achieved coverage distribution and the trajectories followed by the vehicles. We have a budget constraint that says for each vehicle, you have to specify a trajectory, and we know, or we can calculate the incentive that's associated with that trajectory. So whatever you specify, you can't offer too many incentives to vehicles because you have a limited budget. And then there are some feasibility constraints. So these here say, whatever trajectory you give to the vehicle, this should be kind of feasible for the vehicle to achieve. And here we're optimizing over, over which trajectories should we specify for each vehicle. So this is our optimization problem. And if we can solve this optimization problem, we've sort of solved how to incentivize our vehicles, because for each vehicle, we just specify whatever trajectory solves this problem, and we know the incentive we have to attach to it. Now, unfortunately, that's easier said than done. As it turns out, this is an NP-hard optimization problem. And specifically, it becomes a version of a knapsack problem, which is difficult to solve optimally. So instead, we define the greedy heuristic that I've listed here, which we call iLocus. I'm not going to get into the details, but basically the idea is we first choose the time and location that is kind of furthest from the target, so whose distribution is furthest from the target distribution. Then we choose the vehicles that have the best chance of sort of minimizing the KL divergence at this time and location. And then we assign the appropriate incentives to these vehicles. And we can show that this algorithm always converges, that it gets to a feasible solution, et cetera. I'm going to skip over those details. And in the later part of the talk, we'll see that this algorithm actually performs very well. But before I get to the simulation in that part of the talk, I wanted to talk a little bit about how our incentivization algorithm changes when we no longer offer trajectory-specific incentives and we instead start offering location-specific incentives. So if you remember at the beginning of the talk, trajectory-specific incentives are great because you can really control where each vehicle is going to go, but they're somewhat difficult to offer because you have to kind of do this optimization for each specific vehicle, and this may not scale very well to many vehicles. So we started working on this idea of a simpler incentive scheme where we offer the same incentives to all users, and each incentive is attached to giving us data from a certain time and location. Unfortunately, this is an even more difficult problem. So we tried to think about formulating this, but we eventually gave up. And the reason we sort of gave up on a kind of detailed formal model is because when we offer these location-specific incentives, it's very difficult to model sort of how each vehicle is going to react to these location-specific incentives. Because and without that sort of detailed model, it's very hard to optimize kind of what incentives we should offer at every location. So instead we said, well, can we just sort of abstract away from what individual vehicles are going to do? And can we use some sort of machine learning method to abstract this problem complexity and to just say, well, there's a relationship between the prices we offer and the sensing coverage that we achieve. So can we just sort of try to learn this relationship and then optimize our incentives that way? So as it turns out, this is a very nice fit into a reinforcement learning framework. And the idea here is that for each location and time, you can sort of track how much data is remaining to be collected. You can track the number of ride requests, total number of vehicles, et cetera, at each location. So this sort of tells you how likely is it the vehicle will visit this location without any incentives. And then you can just try to learn a relationship between where the vehicles are going to go and the prices that are offered for each location and time. And I'm sort of abstracting over a lot of the details here in the interest of time. But basically the message here is that you can in fact formulate a reinforcement learning algorithm around this idea of location-based incentives. So that's kind of an overview of the algorithms that we use to optimize these incentives. So in the next part of the talk, I wanted to go into a little bit of detail about how these algorithms actually work and how we evaluated them in simulation and experiments. So to do that, we first had to build a fairly detailed vehicle mobility simulator, because again, these are very complex systems. You have a lot of vehicles making lots of different decisions. So let me talk a little bit about that simulator, and then we'll get to the simulation results. So the goal of building the simulator is to make sure that it can include some models or some simulations of how many different taxis behave in this in the city as a function of whatever incentives to offer. So we gave kind of 5 requirements for our simulator. First, we wanted it to build from real-world traffic data, so we wanted it to be as realistic as possible. We wanted to make sure it generates sort of representative ride requests throughout a city so that we can then try to simulate sort of how taxis move according to these distributions of ride requests. Of course, we also had to simulate what are the vehicle reactions to the incentives. So we had to introduce a module that said, here are the incentives we're going to offer. Those incentives would be optimized with the algorithms you just saw, and then emulate the vehicle reactions to them. And then, of course, we wanted it to output the resulting vehicle distribution so we could evaluate sort of what coverage did we end up getting with whatever incentives we decided to offer. So this is a schematic of the simulator. So you can see on the left, we used real data. So I think this was actually using traffic data from Beijing and some ride request data from Beijing as well. And then in the middle, we have what we call these generative models. And these are where we can optimize the incentives offered. We can insert some model of how the drivers are going to react to these incentives. And we can simulate how the drivers are going to behave. And then at the end, we can record sort of what is the achieved sensing coverage given the incentives offered and how the drivers reacted to that. So let me talk a little bit about sort of these generative models, because this is really the heart of the simulator and the heart of the effectiveness of our proposed algorithms. So again, this sort of combines historical features and our knowledge of how drivers are likely to behave. And the idea is if you have, so in the simulator, we were able to kind of simulate ride requests sort of throughout a city, and we used a real road network for the city. And then we were able to kind of simulate what are the driver trajectories through this road network. So for example, here, you can see the driver is coming, driving along this road here because there are ride requests here and here and here. Now, how drivers actually react to these ride requests, we had a model of that for our trajectory-specific incentives, but of course, models can be wrong in practice, so we wanted to make this as flexible as possible. And in order to do that, we said, well, let's introduce different variations of a driver behavior model. So you may have some drivers that are very myopic, that only look at sort of the incentives close to them, only look at the ride requests that are close to them, and kind of ignore what's going on in the broader city. You could have more far-sighted drivers that sort of take in all the information and then try to sort of optimize where should I go given my perception of the ride requests and given whatever incentives your system is offering me. So we built in modules that take into account all of these different driver behaviors. There are also a lot of other secondary behaviors that we were able to kind of insert into these modules. Again, these are very hard to model and optimize over in detail, but in a simulator, you have a lot more freedom to kind of insert factors that affect driver behavior. So for example, if a driver has decided that it wants to get to this destination here, maybe there's a lot of ride requests here, we built in some options where you could specify, oh, the driver wants to avoid traffic. So it's going to take, maybe path A has the least traffic, or maybe it prefers to make fewer turns. So maybe path C, has fewer turns than path B, so that might be preferred. And in order to implement this, we used kind of historical traffic traces, and again, a realistic road network to kind of encode these preferences and how they influence kind of the driver behavior. So there's lots of factors that we were able to build into the simulator that were not really captured in our model, but could be sort of things that would affect driver behavior in practice. All right, this last slide here just shows sort of a schematic of that tries to show that our simulator actually works. So here we're offering location-specific incentives. So we have a 5x5 grid, and at each location in the grid, we offer some incentive for the drivers to go there. So we tried this without incentives, with uniform incentives, that is the same incentive at every location, and then with just randomly chosen incentives. And really what we just wanted to see here is, do drivers react to these incentives at all? So given whatever simulated behavior we have of these drivers, are they reacting to these incentives or are they ignoring these incentives because they're more influenced by other factors? And what we saw is that the drivers do indeed react to these incentives. Remember, these are not optimized incentives. So our goal wasn't to ensure even or balanced coverage. It was just to see kind of, is there some sort of change in the driver distribution? So here, the color of each square denotes the number of vehicles or drivers on each location. You can see that without incentives, it looks very different from with uniform incentives, which looks very different from random incentives. So from this, we concluded that, yes, it is realistic to assume that drivers do react to our incentives, And then our next step was to say, okay, now if we optimize these incentives, can we actually achieve the balanced coverage that was our goal? So that's the subject of the last part of the talk. Okay, so first we started looking at trajectory incentives. So again, this was using the iLocus algorithm, which is shown on the last line here. And here what I'm showing is each plot here is the kind of spatial distribution of drivers throughout the city. And I'm showing this for 5 time steps. So at time step 1, we just started offering incentives to drivers, and we continue to optimize those incentives for 2, 3, 4, and 5. And I'm comparing our optimized trajectory specific incentives to no incentives, which is this first line here, random incentives, which is the second line here, and what we call random selection. So this is kind of trying to approximate prior work where we randomly select some drivers to sense data for us, and then we kind of incentivize them to go to randomly selected trajectories. But our incentives are calculated with our reward model. So we know that the drivers will go to our specified trajectories, but those specified trajectories are random. And you can see, if you look at these heat maps here over space, that our optimized algorithms do in fact achieve a more balanced distribution. So here we define a balanced coverage, balanced distribution as just a uniform distribution over space. So you can see this is definitely the most uniform at this time t equals 5. In fact, if you start looking at the KL divergence, we can show that we can achieve distributions much closer to our targets, not just for a uniform distribution. So this is the uniform distribution here. And again, a lower KL divergence means we came closer to matching our target distribution. So we did better here. We also did much better if our target was a time varying Gaussian distribution. So this shows that these trajectory specific incentives do in fact work. They can in fact achieve these target distributions. Again, assuming that drivers behave as kind of specified in our model and specified in our simulator. Now, there's no guarantee that drivers in practice will behave like that. So we did a very small scale experiment in Beijing, China. So you can see on the left, we integrated our optimized incentives with the existing taxi app. This is the app here. And we just offered these trajectory specific incentives to these taxi drivers and tried to see where they went. So on the right, I'm plotting the results here. So here the y-axis is the coverage quality of the sensing. You can think of this as, how good was our coverage. And you can see in this gray and orange bars, these are respectively the actual deployment and what we would expect from our simulation. And you can see we actually even did a little bit better than our simulation. This blue bar here is no incentives or no actuation. You can see the sensing coverage quality is much worse at all times of the day. So in the last couple slides, I just wanted to show some preliminary results of these location-based incentives. Because again, trajectory-based incentives are nice, but may not be practical at larger scales. So here we implemented our reinforcement learning algorithm. And I'm comparing here no incentive, which is the blue line, to the with incentives, which is the orange line here. And this is called central incentive because we're just using one single reinforcement learning algorithm to determine the incentives offered throughout the city. And this was on a sort of stylized, very small city. This is just a 5x5 grid of locations. You can see that the KL divergence does in fact decrease a little bit over time, and it is in fact better with the orange incentives compared to the blue line, which is no incentives. But clearly there are some problems. So this converges relatively slowly, the results are pretty noisy, and in fact, we would expect our reinforcement learning algorithm to scale poorly to larger cities. So in this example here, this is sort of a larger scale simulation that we did. And here we tried to modify the reinforcement learning a little bit. So it's not just a central agent, but there are kind of multiple agents determining the incentives to offer at different locations throughout the city. This is one way to help deal with the scalability problem. You can see that the KL divergence does decrease, and the sort of noise has gone down a little bit. So we are doing better. But clearly there's much more work to be done because this still converges relatively slowly. And this still was a fairly small simulation. This wasn't up to sort of a big city scale simulation with real data. So the results are promising. The RL algorithm can lead to kind of more even coverage or better coverage, but there's much more to do. And we're still working on sort of new variants of these reinforcement learning algorithms that can help us deal with these scalability problems and kind of testing whether or not we can get the algorithms to scale well to real city scale data. So that's about it. On this slide, I just have a few notes about some upcoming work, and then I'll be more than happy to take questions. Or feel free to send me an email. This is my email here if you would like to discuss further. So as I said, we're working on refining these reinforcement learning algorithms to optimize the prices and incentives offered, particularly looking at scalability problems. We are also working in the simulator to kind of refine our mobility models and our models for sort of how drivers are reacting to our incentives, trying to think of more factors that we could try to build in to make the simulator as realistic as possible. And we also, as part of our UTC project, are hoping to work with more data from robotics in Pittsburgh and TBSI in Shenzhen to get sort of a better picture of how well our algorithms work, not just on this Beijing data that I showed you, but also on data from other partners. So with that, let me stop. And again, I'm happy to answer any questions.
Okay, Carlee, the first question, in the Beijing experiment, did participating drivers report improved daily income overall with this program other than on a normal day?
Yes, that's an excellent question. I think their income did increase a bit. I don't remember the numbers exactly. So they did do a little bit better, but not too much better, because again, we kind of tried to cap the incentives to a maximum budget so that we don't run out of money when offering these incentives.
Okay, can you go into more detail on how you calculated the cost of the original route versus the cost of the modified route? Oh, excuse me, I'm sorry.
Okay, let me
when calculating the monetary incentive.
Right. Let me go back, see if I can, okay. All right, yes, so that was this slide here. Yeah, so basically what we did is, so these are the detailed equations here for calculating the reward. So here, we were just trying to calculate what is the expected driver revenue along the default trajectory compared to the control trajectory. So here, PRC is the default trajectory for vehicle C. And this, this just is summing over all the different potential locations where the driver could end up along this trajectory. And here, this RE is the expected sort of taxi fare of a ride request that would be generated or that would originate at location IJ. And this data is something that you can estimate from historical data on taxi fares. And then we just take kind of the expectation of the expected fare over sort of all possible destinations along this default trajectory. And similarly for the control trajectory, except here, we specify where the driver can be. Whereas here we had some probability distribution of this is where we expect the driver will go without incentives.
How did you implement the real world experiment, integrate with existing taxi apps, get the target destination, display modified route to user, etc.?
Yeah, so that's a great question. So let me go back to that slide. And I'm hiding quite a lot of work that the students did in China on this slide. So one thing we did do here is we simplified our problem a bit by kind of truncating our trajectories. So we said, when we specify a trajectory for a given vehicle, we're not going to specify more than, I believe it was a sequence of 3 locations. And that was helpful both because it made our algorithm faster and it made things a little bit easier to understand for the taxi driver. Now, in terms of how we integrated this with an app, so what we did is we had sort of our backend running that runs these optimized incentive algorithms, and it spits out this trajectory and this incentive for each vehicle. This is a relatively small scale trial. I think there were maybe 10 to 20 vehicles, I want to say, something like that. But for those 10 to 20 vehicles, we added sort of an extension to their app that got the trajectory and the incentive from a backend server, displayed it to the driver, and then allowed the driver to choose, do I follow this trajectory of this trajectory that you specified, or do I not, or do I just go wherever I want? Was that all of the question? I don't remember all the different parts.
Yes.
Okay.
Yes, I have another one. Could this be done with other vehicle types besides taxis, FedEx, Amazon delivery vehicles?
Yeah, that's a really good question. I think, so in principle it could. Certainly you could offer sort of these incentives to drivers and see whether they comply. I think the challenge there would be convincing, say, FedEx or Amazon or the delivery company that allowing their vehicles to sort of be used to do this sort of city scale sensing or city scale services is something that's worth their time and is worthwhile for them. Because obviously their major metric is something like minimizing the total delivery time. One thing that you might envision is you might say, for a given delivery truck, maybe they have a sequence of deliveries they have to do, but there could be some flexibility in maybe the order or the routes that they take between the different deliveries. And there we might be able to offer some incentives to kind of maybe take a little bit longer or go on a different street or a parallel street and get some data that's much more useful for us and offer an incentive to do that. So I think conceptually it's possible. Whether or not the economics kind of work out in practice, that we're not sure about yet.
In a long-term version of the simulator, could the necessary incentives decrease over time? In low coverage areas where cars are incentivized to travel, the incentives may also induce new ride requests. So maybe the driver incentives could eventually approach zero.
Yes, that is a great point. And hopefully that would happen. So that is one thing that that we do want to build in the simulator is, trying to adapt the environment, for example, the ride requests over time. And yeah, this is one of the things that we're hoping could come out of this work, that if we try to keep incentivizing drivers to go to these low coverage areas, maybe there will be an incentive for them to do that without us intervening in the future.
Have you considered other kinds of driver incentives and how your work impacts it, such as things like Rapify, which will incentivize cars to drive into populated areas so their on-car advertisements get more views? Yeah,
that's a good question. I have seen a couple papers on that. We haven't really incorporated that into this work. Actually, I haven't thought about how that relates to this, but that's a really good idea. Yeah, and I imagine there's those platforms are solving a very similar problem to what we're doing.
Have you examined the offset in the increase of incentives by the cost savings in emissions and traffic congestion?
Yeah, that's a good point. So we did not, I have to say. We did consider emissions in the context of, do vehicle emissions sort of corrupt the pollution measurements that we're trying to take on these taxis? So we had a little bit of work there and sort of how you compensate for that. But no, we didn't really measure the overall effect of emissions from our work.
Has this simulation been combined in a test using trip origin zones, previously showing excessive wait times, to combine incentives with latent or unmet demand?
Yeah. Right, so that is one thing I think we could do with the current version of the simulator. We do have some traces of sort of taxi demands, wait times, and travel times. I don't think we have actually measured that, but it would be very doable and it would be very interesting to see those results and how they come out of the simulator.
That was all of the questions that we have.
Awesome. Okay. Yeah, so again, I'm happy to stick around if there are other questions now, or please feel free to get in contact by email. I'm happy to discuss this further.
Thank you very much, Carlee.
Okay, thank you so much for having me.
All right, thank you, Carlee, for sharing your work. And to all of today's attendees, thank you for joining us. As I mentioned earlier, today's presentation will be posted on the Mobility 21 What's Happening page of the website, along with a link to the video of the session. This afternoon, you will be receiving an email asking you to take a short survey about today's SMC. Please take a few minutes to provide your feedback. For students who are interested in engaging in transportation topics, the Transportation Club on campus is a great way to plug into transportation topics with fellow transport nerds. Again, thanks for attending today, and please feel free to contact us with any questions.